Hello, my name is David Fowles. I'm currently an undergraduate at the University of Utah in my senior year studying physics. So I'll be graduating actually this December in just a couple of weeks with my bachelor's degree in physics. And I've been working on this specific project under the guidance of UROP, the Undergraduate Research Opportunity Program, for the past year and a half or so. I'm completing my second semester of UROP, and I'm very grateful for the opportunity I had to complete research on a project that I was very passionate about. Both the opportunities granted to me by UROP itself and, of course, by my mentors, Dr. Pucha and Dr. Mao. My project is on comparing the spectra, specifically of changing-look AGNs, and I'm going to give a brief overview about all of the things that I've learned over the past year and a half. So before I get into changing-look AGNs, I first have to address what are intermediate mass black holes. So we know that stellar mass black holes form through the death of stars. You can see on this graph that they are under 100 times uh, the mass of the sun. And then supermassive black holes are found at the center of all massive galaxies. So an example of this would be the Milky Way. Our own Milky Way, where we reside, has a supermassive black hole at the center of it. And these supermassive black holes are greater than 1 million times the mass of the sun. But somewhere in between, we suspect that there are these intermediate mass black holes. So they reside, they have between 100 and 1 million times the mass of the sun. So very wide range there. Um, the problem is that we can't actually find any. We suspect that they exist because due to the size of supermassive black holes today and the known age of the universe and the known rate that black holes grow, if a stellar mass black hole had formed at the start of the universe and then had grown over the course of the universe's age, it wouldn't have been able to grow into the size of the supermassive black holes that we see today. So we suspect that there are these intermediate mass black holes, and they are the seeds for the first black holes that we see now as supermassive black holes today. But there are very few candidates for these intermediate mass black holes that have been confirmed, but we do know that they exist. Studying these intermediate mass black holes will hopefully provide clues about the very first black holes formed in the universe and how they grew into the supermassive black holes that we see today. So now I can get into what exactly are active galactic nuclei, or AGN. The problem with finding black holes, both intermediate mass black holes and other ones, is that they can't be observed directly. Black holes are so massive and have such a strong gravitational force that they prevent even light from escaping them. And so we can't actually see them. Instead, we can see what is called the active galactic nuclei, which is the region around the black hole that it interacts with. So in this image that I have on the right, you can see right here in the middle is the black hole. And then around the black hole is the accretion disk. So matter accretes directly onto a black hole, which releases a huge amount of energy, and this triggers the active galactic nuclei. Other important things to note in this is that these little clumps here are the broadline region. So they're located within the obscuring torus, which is a large region around the accretion disk and around the broadline region that is full of dust. And so when we look at the black hole edge on, so if you're looking at it from here, the torus can get in the way of seeing the black hole, the broadline region, the accretion disk. It can be very annoying to deal with. Whereas if you're looking at it from up here, if you imagine looking down on the black hole, you could see the obscuring torus as a donut around it, and then the broadline region and the accretion disk. But like the Earth has a very distinct axis that it rotates around, black holes are the same way. They don't do this. And so if we're stuck looking at it edge on, that's not going to change. But it's important to realize that different regions of an active galactic nuclei or a nucleus emit different signatures that can be studied and understood via an optical spectrum. So getting into what an optical spectrum is and what spectra in general are, I'm sure you're all aware that white light is, if passed through a prism, can be spread out into a rainbow. This rainbow that we see is the spectrum of the white light. And so the different colors have their own distinct wavelengths that we can view. Um, and then this rainbow is the spectrum of that white light that is passed through. Similarly, we observe light from a galaxy, and then we can break that light up via a spectrograph into the galaxy's individual spectrum. And so I have here a zoomed in region that goes from about 4,000 angstroms to 7,000 angstroms in wavelength. Um, from Dr. Prucha, my mentor, she did this graph that shows the optical spectrum for a specific galaxy. And you can see there are narrow line regions, so called narrow line regions because they have these very narrow spikes that go along them. And then there's a broad line region present here in the H alpha region, which is this area under the curve here. So they're named as such just because of the nature of how the lines appear in the spectrograph uh, after it's been analyzed. So the narrow line regions are these very spiky regions, and the broad line regions, which are located behind the obscuring torus, are these areas that there's a more distinct area under the curve. The way that we examine galaxies is via telescopes. And the two telescopes that I chose to use are the SDSS, or Sloan Digital Sky Survey, and DESI, which is the Dark Energy Spectroscopic Instrument. SDSS has been running since about the year 2000, has performed several iterations of data and has provided I think up to about 1 million um, galaxies, or the spectra for about 1 million galaxies that we can observe. DESI has only been running since about 2021, but already it's provided in its first release of data over 10 million galaxies. So the science and the technology is a lot better now with DESI than it was with the SDSS when we started out. We have a lot more galaxies to pull from now. But my purpose, so now I kind of get into what my exact purpose was with my project. My purpose was to examine galaxies that had been observed both by SDSS 25 years ago and DESI, observed just a few years ago, and compare them and see how the spectra of galaxy changes over time. Doing this can teach us about how galaxies evolve, um, and especially how that obscuring torus affects uh, the spectra. So I have here a graph that I've created of the spectra from one galaxy. So this is the same galaxy, this spectra. Uh, it's the spectra is for the same galaxy for both of these lines, and it compares them. So we have the SDSS spectra in blue, and that was taken in the year 2000, and the DESI spectra in red, taken from the year 2021. And this is where we can define what changing look active galactic nuclei are. So you can see, looking at the two spectra, that they are inherently different. There's more flux in general for SDSS. There's less for DESI. This could be because there was more dust in the way or more obscuring things happening, a wide variety of regions or reasons. The important thing with Changing-Look AGN, though, is that the broad line region that we mentioned earlier, so this region here, this wide region under the curve, and then it appears here as well, a very wide region under this curve, either appears or disappears. And this is called the broad line region either being turned on or off. So in SDSS, you can see for both H beta and H alpha, which are two elements, those are two wavelengths for those specific elements. it either it's turned on for the SDSS. It's very clear that there's a broad line region here and a broad line region here. Whereas for DESI, there's almost no broadline region here, and there is a broadline region here for H alpha, but it's smaller. And so the look of the AGN, how it looks, changes significantly just over 20 years. And galaxies don't normally evolve that much over 20 years. So something is happening to cause this change. A closer look at this region. So this is specifically zoomed in at on the H beta region for that same galaxy. So again, SDSS is shown in blue and DESI in red. The broadline region is here for SDSS. There's a significant curve. And then for DESI, there's almost nothing. You could almost just mistake it for noise. So we know that the galaxy itself isn't changing by all that much, but the spectra is. One reason that this might be is again because of the obscuring torus. It was originally believed that the obscuring torus was like a single solid donut shape that surrounded the accretion disk and the black hole that prevented us from viewing the black hole, the accretion disk, and the broadline region. And so there was, not really any hope for seeing the black hole itself if the obscuring torus was in the way. But with these two galaxies, you can see that you can see the broadline region in one of them. Again, this is the broadline region, and then you can't see it in the other one. This means that the obscuring torus may not be what we initially thought it was, which is a single solid donut. Rather, it could be clumps of dust gathered around. This image actually shows a very good example of, maybe what it could look like, where maybe it's solid all the way around, but then there's a big clump of dust missing right here that we can see through it and visualize the black hole and the broadline region. And maybe this is what the image looked like for SDSS that allowed us to see that broad line region. And then over 20 years, the galaxy rotated so that, imagine it rotating so that the back of the obscuring torus is now facing us. We can no longer see that because the obscuring torus is now in the way. So sometimes we can peek through that obscuring torus and see what's happening, and sometimes we cannot. I zoom in even closer here on the H beta region for DESI and SDSS just to show even further that for SDSS, I completed these Gaussian fits, and the best fit for SDSS was including both the broad line region and this narrow line region, the little spike. And then for DESI, it was just the narrow line region. That spike there was the only thing visible. You can see that the width and the height of the spike are about the same for both SDSS and DESI. So the narrow line region, shown here, not affected by the obscuring torus, is still visible in both spectra. But the broad line region affected by the obscuring torus is not visible. And then I've also calculated from the Gaussian fits the full width half max, which is a metric that we use to measure how wide that area under the curve is 94 kilometers per second for SDSS and only 5 kilometers per second for DESI. So much smaller because this width is much smaller than it is over here. Same thing happens with the flux. Flux is a metric used to describe the area under that curve. So all of this region here and this little region here. Whereas for DESI, it's just this little region here. And there's significantly more flux in that region for SDSS than it is for DESI. So it's very clear that these spectra are different, even though they were taken for the exact same galaxy and only 20 years apart, which is a very relatively short time. So my conclusions for this are we've seen how spectra for these same galaxies taken 20 years apart show a significant difference in the H beta profile. And then the Gaussian fitting confirms this. The SDSS spectrum only exhibits, or the SDSS spectrum exhibits both narrow and broad components, while the DESI spectrum only shows the narrow component, further cementing the idea that with the disappearance of the broad component, there is some obscuring torus that we can sometimes peek through and sometimes not peek through. And occasionally we can see the broad line region and occasionally we cannot. So this makes it really hard to identify intermediate mass black holes because we don't know whether or not we're able to see through the obscuring torus at that time. But this research is very helpful in that. The code that I completed was only implemented for this specific galaxy that I found to compare the two regions, but it can be applied to millions of galaxies that have been found both by SDSS and DESI, um, or any other surveys that may occur. You can take this code can be implemented to all of them. And so this will help us to reach a much larger data set, find more intermediate mass black holes, find more candidates, and hopefully understand the obscuring torus and the nature of active galactic nuclei more, which will allow us to understand how the universe around us evolves. But thank you for tuning in to my project. Again, I was very happy to for the opportunity that UROP presented me to complete this project, and I'm excited to continue my research in this field.